bienvenidos a esta charla del día de hoy acerca de el permafrost de montañas tropicales, que será impartida por el profesor Kenji Yoshikawa, quien nos está visitando de la Universidad de Alaska en Fairbanks. Es un tema sumamente interesante para todos, fundamentalmente porque es un tema que, si bien se conoce desde hace muchas décadas, es un tema que está tomando cada vez mayor interés, y no solamente en la región latinoamericana en general, o en México en particular, sino porque muchos aspectos que tienen que ver con el cambio climático a nivel global, particularmente en las zonas más nórdicas, en donde hay fusión del permafrost y la liberación de gases como el metano, etcétera, están provocando una serie de efectos, y lo mismo también desde el punto de vista de infraestructura y construcción. Pero necesitamos saber más de qué es esto y cómo se comporta en otras regiones, no solamente en las zonas nórdicas, porque también en las montañas, desde México hasta Tierra del Fuego, este es un proceso muy importante. Y qué mejor que tengamos hoy a nuestro ponente, al profesor Yoshikawa, para que nos hable de ello. El profesor Kenji Yoshikawa tiene una preparación muy importante desde la Universidad de Hokkaido. Él estuvo en el Departamento de Ciencias Ambientales con énfasis en hidrología de pingos, uno de esos rasgos periglaciales que son importantes. Por el otro lado, también en la Universidad de Hokkaido, en el Departamento de Ciencias Ambientales, ahí también hizo su doctorado en 1997, con énfasis en los procesos periglaciales. El profesor es hoy en día profesor en recursos hídricos en el Centro de Investigación del Agua y el Ambiente en el Instituto de Ingeniería del Norte en la Universidad de Alaska en Fairbanks. Eso desde el año 2010 hasta el presente. Y ha encabezado la Asociación Internacional de Permafrost, básicamente el Comité de Educación y de Divulgación. También ha estado a cargo en la Universidad del Ártico en una red temática sobre permafrost. Él ha recibido, debido a su amplia experiencia y la publicación de más de 100 trabajos en revistas indexadas, él ha recibido el premio de honor del rector de la Universidad de Hokkaido en Sapporo en 1994, y ha tenido el premio por servicio ya conocido como Emil Usibile, de la Universidad de Alaska en Fairbanks en el año 2012. Debo decir que en lo que se conoce como el Grupo de Trabajo de Nieves y Hielos que patrocina la UNESCO, existe dentro del Programa Hidrológico Internacional este grupo, y este grupo desde hace un par de años ha venido organizando una serie de subgrupos. Uno de ellos es justamente el subgrupo de suelos permanentemente congelados, y que se está abocando actualmente al estudio de los procesos periglaciales. Y en este grupo colabora de una manera muy importante a lo largo de toda Latinoamérica con los colegas tanto mexicanos como de Colombia, Ecuador, Perú, Bolivia, Chile y Argentina. Entonces, el profesor Yoshikawa es nuestro gran conocido, un gran amigo, y al que le vamos a pedir que por favor pase a dirigirnos la palabra de su charla, Tropical Mountain Permafrost. Por favor.
Thank you. Thank you, Hugo. Good afternoon. My name is Kenji Yoshikawa. I'm a professor at the University of Alaska Fairbanks. Thank you for coming today. So I'm talking about mainly tropical permafrost in tropical area. Then there is several point of view about permafrost because sometimes you thinking the why the permafrost is important for the high mountains people not living. But I think there is several point I should mention, but mainly today I think importance is number one is the indicator of the climate, especially the you see the higher mountain today, the glacier is melting and also a lot of different environmental changing. How to monitor, how to archive the climate for the high mountains. Glacier will be disappear, then we cannot monitor anymore. But permafrost or ground is still remain there, but temperature will be changed. So that means we should establish long-term temperature monitoring in the ground that we can see the today still frozen, but in the future maybe the thawing then plus temperature, but still we can monitor continuously. So that means that we can see the climate change for the long term for the using permafrost. So then second point is water. We have a lot of drought problem in the on this area. So then mainly the water came from the glacier melt water. Then if the permafrost is absent, groundwater going to the percolate, go to the groundwater system, then maybe the submerged to the ground is many, many long years later. Then if the permafrost presence, we can go to the groundwater groundwater system because permafrost is impermeable. So that case, completely hydraulic environment different presence or absence of permafrost makes big difference about water pathway. So that's why we try to understand more how permafrost distribute in the mountain area. So then this is one of the, but before we talk about the tropical, what is really tropical? We have to define about that. Then maybe the most typically people understand the tropical is something like latitude 23.5 for the tropical Cancer to the tropical Capricorn. Between this area is people thinking about tropical. But this is very much very straight line. Then actually the geography of the Earth is not following this straight line. This is very much the solar radiation issue, right? So then if we, even between this, we put in the mountains for the, all the for the high mountains, you can see the Hawaii has a over 4,000 meter Mauna Kea, Mauna Loa. Then Mexico has several mountains. Then many mountains, high mountain Andes. Then beside this area, there is some, for example, the Kilimanjaro. Then Mount Kenya is not just a little over 5,000, but not too high. Then Ruwenzori. Then also these are all 3,000, 4,000 meter, then less than 5,000 meter. So that means it's not too much mountains, high mountains in the tropical area, but especially this area has Latin America has a lot of high mountains. Then we try to understand the mountains about the permafrost. You can see the red triangle. This could be permafrost. Then blue angle may not too high enough or some other reason. So then another thing is very interestingly, these mountains most likely is volcanoes. So then now we're talking about what is tropical. So then we can talk about possible to the just latitude 23.5 north to 23.5 south. But when you look at the more environment issue, maybe itchy, like this is a like hadron circulation of the Earth for the low pressure system is staying in this area. Like for example, the northern hemisphere's trade wind, for the southern hemisphere's trade wind, both meet together. That's usually bad weather. So that's is one of the definition of the tropical between this summertime itchy to wintertime itchy. Between this area could be the good candidate about the definition of tropical, especially the glacier people doing this because each makes a lot of precipitations. So then another, that's one of the important for permafrost issue. That, for example, for Mexico, we have more precipitation in the summertime because this hitting for the Mexico. Then winter time, it is more south down. That means that we don't have much snow. So then another potentially definition of the tropical, maybe the daily temperature amplitude is more than the annual amplitude. So that case, we can see that this red line here, you can see that most of the Mexico has a annual temperature variation is bigger than the annual amplitude. Then most of the Andes too. So this is kind of another good candidate about the definition of tropical. But one of the problem is, for example, for the like Amazon area or something like that, equator. Anyways, the annual temperature variation is not that big, but still annual temperature is not that big. That's relatively both smaller. That end up to this fitting. But if you go to Mexico City or like southern Atacama Desert, it's definitely we have a season here, but the annual temperature is much bigger. They end up to go inside the tropical definition. So that means, again, when we defined about what is tropical, it's kind of not easy. Could be the solar radiation, could be the precipitation pattern, could be the temperature variation issue. That's typically these three definition we talking about, defined about tropical. But if we're talking about permafrost, little more different. I want a little talking about more vertical structure of the Earth. Then you can see that this is the equator here. So then go to the northern hemisphere, southern hemisphere. This is elevations. I put several mountains that we are monitoring. You can see the like Pico de Elizabeth here, the Mauna Kea, Hawaii, or Denali for Alaska, or like K2 or the Himalayas, or the Chimborazo or Kilimanjaro. You can see the most of the mountain here. That about this here. So then when we have our permafrost monitoring for these mountains, we can see the tropical, I think more the like blue color is east wind. Then yellow color is more like west wind. So that means that this is jet stream. Extreme jet stream is very high altitude, latitude about 30, 40 degree south and 30 to 40 degree north, has a very strong jet wind, jet stream always. So then jet stream areas are definitely not tropical. Then more like east wind side is more tropical. Then when you look at, for example, Pico de Elizabeth, kind of between, but this meaning this is the annual average of the wind pattern. So then when you look at the seasonal, when Pico de Elizabeth, we have more jet stream we can affect by the winter time. So then summertime, more like east wind area. So that means kind of edge of the jet stream is kind of boundary of the tropical. That's I feel like for the permafrost temperature patterns. So before I go to more further into the permafrost, make sure that again, I earlier mentioned about permafrost is in tropical areas coincidentally located on the volcanoes. Then this is Kilimanjaro. Kilimanjaro has still active volcanoes. There are lots of geothermals. You can see the glacier has a annual pattern. You can see the not parallel to the ground, meaning heat, now the Kilimanjaro is famous for disappear for glacier, but not just from top. The bottom melting we can see at the Kilimanjaro, meaning we don't really have a permafrost good conditions. This is several borehole sites for Kilimanjaro. We found the permafrost for the very edge of the crater, but around the crater, you have a lot of, this is 1 meter below temperature, 18 degrees or plus 13 degrees, very hot geothermal we see. Then, for example, nighttime, if we nighttime, if we're using infrared camera, this is daytime. Like you can see the caldera here for the Kilimanjaro, 5,895 meters. Then nighttime, same pictures, you can see a lot of red spots. These are very hot temperature. Then some of the places you can see the over 40 degrees C. So that's Kilimanjaro has a lot of geothermal from the volcanic activities. For example, this is my borehole site. Then these borehole very hot, no permafrost. But I found the permafrost here, very far from the geothermal area. Then also there is glacier here. Then next of the glacier, at least this area has open for the littoral age time. So that's meaning, so when you look at the permafrost in the volcanic area in tropical, tricky part is number one, we have volcanoes, a lot of geothermal issue. Number two, there is usually ice capped before, like a littoral age time, a lot of glacier covered. Then typically glacier, under the glacier has not much cold enough. So the nice have a non-glacial area has a more chance to have a permafrost. So we have to think about volcanic activity and glacier cover issue. So then when I look at the tropical areas permafrost, there is a little more, when you look at the detail, little more two different areas. Number one has like just below the equator, which is completely zero seasons. Then another one is seasons, like here, Mexico City, about 90 degrees north. Then also something like Atacama is 20, 25 degrees south. That all the area has seasons. So that means if we have a presence of season or absence of season has a big difference about permafrost. Then this is Kilimanjaro temperatures for the site for permafrost. Then you can see the 3 meter below ground still zero. But when go above this, when we have a snow, like El Nino year, Kilimanjaro has a very little snow. So that means, like for example, less than 1 month of snow cover, ground surface temperature reaches almost close to 3 degrees C. Then instead, if we have like 7 months of snow cover, you can colder than -1. So that means that depend on how long you have a snow cover on the mountains, you have a ground temperature has a very strongly affected for the upper 2 meter. So that's equator region's characteristic. Then different meaning. Again, yeah, we don't say the season for the equator, but there is a wet season and dry season, not like solar radiations. Then wet season, which is snow covered, we have a typically, like, for example, Kilimanjaro, the top is -7 degrees C for the air temperature. Then that's kind of straight go penetrate so that we can have a permafrost. So then if the dry season, ground has a huge surface offset. Air temperature is -7, but the ground surface temperature is positive. So that case, we don't have a permafrost in the upper layer, or even continue to this dry season, we will disappear permafrost. So that's the pattern of the equator region. Then how about between the Kilimanjaro or Chimborazo or something in the equator region mountain versus Pico do Reservoir for like here, where is the boundary for the season or non-season? So you can see that this is typical solar radiations versus the latitude. You can see the like equator for the most strongest solar radiation, about 400 watt square meters per square meters. That's about spring and fall. Then not December, not June. Like spring and fall, the biggest solar radiations. So then when you go to the about 10 degrees south and north, you can see that this is switched to the by seasons. So maybe a little hard to see. This is more, maybe it's just easy to see that how looks like, for example, latitude 3 degrees south, we have 2 peaks of the solar radiations. Here, of course, we have only 1 peak. For the summertime is highest, wintertime is lowest. But if the equator region, we have 2 peaks, not strong, but there is 2 peaks. So that's a big difference to the equator tropical mountain versus subtropical Mexico, Atacama areas pattern of the temperature. So that means that when we look at the permafrost, this equator permafrost versus subtropical like Mexican permafrost is a huge pattern difference exists. So then this is, for example, I can show this is Hawaii, Mauna Kea. We have only 4,000 meters, we have permafrost. Only 2 spots we have a borehole. Very little patch of the frozen ground exists like this. So then I'm working here very closely detailed. And this is, for example, the time series of the temperature variation is upper 70 centimeters. Then this area is always thawed. Then below this red line is permafrost, frozen all the time. Then you can see the Hawaii's Mauna Kea is 90-degree north, which is exactly same like here in Mexico City, or Pico de Orizaba. So that means similar like season patterns. Of course, winter time, all layers frozen. Summertime, up 60 centimeter is thawed. Then below 60 centimeter is permafrost. That's in Hawaii. Then I believe here very similar. So then we see the very interesting things is here. Do you see that when the spring comes, we have a seasons, start sowing ground gradually like this. Then and to the June, like that means like April to June, July, slowly thawing, which is a conductive heat transfer to thawing the ground. Then summertime thaw, then interesting is here. The end of November suddenly freeze all layers, not the conductive. So that means we have some convection freezing process going on at the Hawaii. If we don't have here, we don't have a permafrost. So that means very interesting thing is we need to have a winter for Hawaii. So that means same thing here. We need to have a season. We need to have a winter for keep the permafrost in Mexico. But remember that in Kilimanjaro, we don't need a winter. We need just snow cover. So that's a big difference for the Kilimanjaro and Mexico or Hawaii situations. So then again, this is another very high resolution temperature for the day for the upper 40 centimeter in Hawaii. Like some summer day, like you can see the middle of the day to middle of night. You can see temperature variations, of course, go into the ground. Variations are smaller, then 40 centimeter, almost no variations. So then this last 2 pictures, interesting. See that this is March 16. Above ground is only 3 centimeter is thawing. Then all layers kind of stay zero. So that means very much ice field, all the matrix of the gravel has ice. So this ice developed with the winter snow melt water. So if we don't have a snow, if we don't have a winter cold, we don't develop this ice matrix. So that means you can keep the permafrost. So then after April, 1 month later, thawing front reached to the almost 20 centimeter. So that means every springtime to summer, this ice give a lot of latent heat consume. So they end up to the protecting for the permafrost. So that's we see in Hawaii. Then I'm believing like Nevado de Toluca or something similar like rock glacier type of the metric similar condition exist. That's why we try to hoping to searching the Mexican mountain too. So then this is another topic, when you look at this is the Incas, like Johann Reinhardt has a hard work for looking for the mummies in the Inca. This is Ampato, south of Peru. We have a huge difference for this is 1999, a lot of glacier, but looks like sublimate a lot for the war. Then this is the last year when I was there, same spot. You see the almost zero glacier. Then at that time, 1999, they digging for the mummies is full of the ice-rich permafrost. So they are very difficult time for digging because all the metallic field in the ice. Then I have a little question about, this is Inca time, how they dig ground. They don't use a shovel because they are not allowed to using metal for this ceremony. They only use wood. So the wood shovel, you can dig the ice-rich permafrost. Right? So how can they did the mummy, they put in the ground, in the permafrost. So then we figure out this is one of the site we are visiting about Uayaco, which is north of Chile. Another thing, they put in the 3 child body in the ground about 3 meters below. 3 meters digging permafrost is not easy at all, even 500 years ago. But they did with wood. How can do? We are there to see, understand, is no ice. So it's so easy to dig because it is frozen, but no ice, dry permafrost. So then we believe the Ampato is the same thing. 500 years ago, we have a completely dry permafrost, easy to dig, they put in the ceremony. Then, but today, all ice-rich permafrost filled in the matrix of the soil. But Uayaco is 6,700 meters high. So that means this side is still similar environment than the 500 years ago. So that means the dry permafrost. So then that's very makes interesting about what is the permafrost's condition for by the altitude. That's we are a little more looking for especially for the high mountains. You can see that this is one of the world's driest place on our planet. So then we pick the Ocankilcha, Chacnanto, this is the Aruma for the telescope site. Then Uayacos, Ojo de Cerrado. Ojo de Cerrado is the highest mountain in the world. Also second highest mountain in Andes. So these mountains, we have a borehole now. Then we monitor the site, and this is one of the very brief my result. You can see the very low elevations, seasonal frost start, but the summertime was some reason to thaw temporary, but there is some sporadic permafrost exists. Then little more higher, we call lower limit of alpine permafrost, meaning all year round the permafrost exists for the on terrain. Then lower part of the permafrost area has always ice rich that we figure out. Then typically snow going to penitentes for the very like that. Maybe later I can have some pictures, but these shapes they go a little more higher, going drier, then really upper height, like higher than 6,400 meters of the Andes we have a dry permafrost, like that time Incas, they dig ground for the mummies. So then you can see that if that this high, you don't have a penitentes anymore. We thought the penitentes is a very high solar radiation to develop all the way to Andes. It's not true. That's penitence limit is about 6,400. So then above this, we really don't have no liquid. So that's the pattern of the zonation of the tropical high mountains. So then this is one of the picture of the summit area of the Ojo de Cerrado, like 6,700. You can see the no penitentes for snow, like patterns. This is all the aberration pattern of the sublimation. Then they don't melt snow. All the snow going to sublimation. That means permafrost is completely dry. So then this is a upper 70 centimeter of the ground temperature profile for the most warm day of the summer and the most cold day of the winter at the Ojo de Cerrado. So then this is the highest near the summit. You can see the active layer is only few centimeters of the surface. Then below this is the permafrost all the way, all the year round. Then important thing is there is a season in Ojo de Cerrado because almost 27 degrees south. But active layer is only duennial, not seasonal. So that's a very important point we find out. Then when you go to a little lower elevation, 5,800, still no seasonal, only duennial active layer. But deeper than that 3 centimeter, over 3 centimeter, about 10 centimeter summertime. But the winter time always frozen. Then when it goes more lower, 5,200, we have about 50 centimeter of the active layer. Then that's the seasonal. So that means like many permafrost researchers thinking about the seasonal active layer as seasonal. That's very much the higher latitude, like Alaska, Siberia, Canada, or Antarctic. These people, everybody talking about active layer is seasonal. But when you look at the high mountains or tropical high mountain permafrost, is most likely active layer as a duennial. That's big difference. Then when you look at the duennial, very interestingly, for our solar system, like Martian permafrost is duennial. Then also at the moon, like moon, you know that when the sun hit the moon surface, going to the 100 degree Celsius, then when the shade side is minus 200 degrees Celsius, big temperature variation, like 300 degrees changing, but the 50 centimeter below is frozen like minus 17 degrees C all the way year round. Then only the active layer for the duennial, for the moon. So the moon, Mars, almost all the planet, including our planet, active layer is typically duennial. But some reason our permafrost area in the northern, southern, or high latitude is seasonal. That's very interesting point of view. Then when we have a duennial active layer, what happens is very high freeze-thaw cycles, like above zero, below zero, almost every day. You can see this is two sites for the Atacama region. You can see the ground surface is over 200 times freeze-thaw cycles. Then little more higher elevations, 120s, then goes deeper the ground. This is the duennial active layer site. I mean, the only 15 centimeter below ground is frozen all year round. Then that's why the freeze-thaw cycle is dropping dramatically for this. So then this makes very different than the high latitude like Alaska or Siberia. So that makes end up to that you can see the beautiful stripes or many periglacial process going on because freeze-thaw cycle is very intense. So that's a very different than the compared for the high latitude permafrost versus tropical permafrost. So then this is a in little more talking about Mexico. Then where is really Mexican permafrost exists? That's last 20 years ago that we worked together. That's the biggest question. So then, so this is we try to put the ground temperature profile, the annual mean ground temperature for that to the makes lapse rate. Then this is a the Popocatépetl, but this is active volcano, then very access is limited for high area, then not really nice line. But the rest of the all lines, this is a Pico de Orizaba, this is Iztaccíhuatl, almost the same for the crossing zero is 5,000, little higher than 5,000, about 5,030 or 5,040 meters. Then south side of the Pico de Orizaba is about 5,300 meters crossing zero. This is about idea of the lower limit of the permafrost in the Mexican mountains. Then this is put together of all the this is elevations versus 4 mountains. Then our star mark is all our monitoring site. Then we found the permafrost here. Then maybe around here. Then somewhere around here, the permafrost boundary. So that means somewhere around 5,200, 5,100, around here is the boundary of the permafrost, we think. So then one of the biggest confusion happened for the Mexican, because Mexican permafrost study is one of the longest history of the Latin America. Many Europeans come here earlier time, then they study Mexico very intense. So that means same time we have a little more confusing happening. So for example, this is a Aeroco glacier for the Iztaccíhuatl. You can still see the big ice bodies. Then early time we consider this is permafrost, but actually no, we should not say permafrost, but many literature say permafrost. So that's one of the problem about this. And I need a little explain about this. So this is an early interpretation of the lower limit of alpine permafrost. There is glacier there. Then of course, the lower part of outlet glacier has a debris covered. Then anything you see the ice, especially like 60s, 70s, 80s, we don't have a data logger. We don't measure the temperature all year round. So that means the most likely scientists go up to the mountain. If you see the ice at the field, they describe permafrost. But the ice could be just frozen in the morning. Ice could be just outcrop of the glacier ice. But just to describe a permafrost, that's the early times interpretation. That means the darkest lower boundary permafrost reaching here. But this is a light definition, especially in 1995, Charles Harris and William Burton has a nice description of this problem. Then now it's here. So that anything, ground frozen all year round, we call permafrost. But when you have a glacier ice, debris cover is thicker than the active layer. We have a permafrost. This is ice, is glacier ice. But the glacier ice is above the glacier ice, debris thickness is thicker than active layer. We have a permafrost. Then if the debris cover is thinner than active layer, we just call it buried glacier ice. This is not the permafrost. So these two exactly same ice, but the thickness of the debris is different. So this is very important for me or for our community. In that case, all this area we're talking about permafrost, it's not permafrost. So then how we important for this? Because this ice is slowly, very slowly, but degrading, right? Because thermal balance is not equal. So that means the ice is slowly melting. because latent heat is using a lot of heat. But this debris cover is thicker than the active layer, meaning summer heat doesn't reach to the ice surface. So that means the ice could be just stay longer or more stable. So that's a very different stability of the ice. So that means we should say the lower limit of the alpine permafrost is here, not the previous here. So that case, every definition could be changing for the, like many times, like Istashigwa, lower limit of permafrost like 4,800 because Aoroko glacier exists. But we should say more like 5,200 close the high. So that means much higher than the we previously thinking about permafrost lower limit. That's I think in Mexico case. So again, this is actual monitoring for temperature. We don't have much monitoring, but we got to help me to we try to develop more permafrost monitoring site in the future. So this Popocatépetl Iztaccíhuatl to the Pico Reservoir. We only get the permafrost confirmation is south side of 5,300 meter of permafrost. Stay zero, even 1 meter below. But the rest of stuff is positive temperature. So we try to more find the spot. So this is summarized about the Mexican permafrost structure for the compare those mountains. So there is something like a lower limit of the frost limit. Then some sporadic permafrost could be exist like north side of Iztaccíhuatl or the Nevado de Toluca for the rock glacier like Lorenzo does a very good job about Little Ice Age has a very active rock glacier exist. Could be some ice remain somewhere. Then no permafrost above this. Then previously people talking about permafrost is maybe just glacier ice. Then there is a lower limit of permafrost somewhere around 5,100, 200. Then most of the like this is the idea about like Pico do Reservoir area here. The north side facing has a glacier ice. Then some permafrost exists. So then this is very much the last summary. So definition of the tropical, there is a glaciologist say the 3 different, like tropic Cancer, Capricorn, or each area, or the annual versus annual temperature amplitude. These are also good candidate about definition of tropical. But for the permafrost, important thing is solar radiation was about 10 degree to 11 degree north and south season changing, the solar radiation pattern changing. That's a permafrost presence pattern changing. So that's another issue. Then also wind. Anything you hit the jet stream in the winter time, but summertime no jet stream effect. That's maybe the limit of the tropical. Then also we have a strong vertical zonations, especially you see the Inca time. You got very high mountain, we have a dry permafrost. Then lower limit of the alpine permafrost usually much more wetter, much more ice rich. Then maybe some of the sporadic permafrost exists, maybe very lower part. So then also the permafrost has a very much the volcano or glacier interactions. We have to be careful and think about the glacier chronology is very important idea about the presence or absence of permafrost. Then finally, yeah, we were very interested about the cultural interactions, especially Incas. Then I think Mexico has a very long history too. Then maybe we don't know yet, but maybe like Iztaccíhuatl, Popocatépetl, or maybe even the Pico do Reservoir, something cultural interaction and permafrost in the future, maybe interesting topic to understand. Thank you very much.
Arigatou gozaimasu, Yoshikawa-san. Muchas gracias, Kenji. No sé si hay alguna pregunta aquí en la sala. Por favor, quienes están conectándose vía internet en Facebook Live o en YouTube, pueden hacer sus preguntas a través del chat y quienes están a través del Zoom pueden levantar su mano para que les demos la palabra y pueden hacer su intervención directamente. ¿Aquí hay alguna pregunta? ¿No? Porque yo tengo un montón. Franco HM en Facebook Live nos dice, very nice talk. How is the increase in temperature affecting the permafrost in the mountains of central Mexico? And is there hazard map in relation to it? Again, the question, how is the increase in temperature affecting the permafrost in mountains of central Mexico? And if there is a hazard map.
Yeah, thank you for the Frank. I think that, honestly, we thinking this is very important issue to think about the hazard and the temperature increasing. But honestly, we don't continue to long-term monitoring yet. That's why we try to establish for the understanding this issue. So that in this moment, we don't know how is last like 10 years to 50 years of temperature changing. But at least we can see the glaciers retreating that we know it. Then that case temperature thermal balance is changing for the ground surface, which is permafrost is could be decreasing, but we don't quite understand that this mechanism. I mean, glacier retreating versus permafrost changing. We don't know yet.
Yes, I should mention that Victor Hugo Soto made his PhD thesis just trying to understand the distribution of temperatures in particularly at Pico de Orizaba. But still there is a lot to do, and there is an open invitation for anyone to participate in that. There is another exactly for the group of Victor Soto. Thanks for coming to Mexico, Professor Kenji, and for sharing your knowledge regarding this great issue. Okay. Okay. I have several questions actually. How much the differences between the climatic change can be detected at these boreholes, for instance, at Kilimanjaro, and how can we differentiate from increases in temperature due to the volcanic activity? Sometimes the volcanoes change very quickly, and it could be very easy to understand, particularly when fumaroles appear. But when the temperature, particularly at the places you showed in Kilimanjaro, the changes could be subtle. How to differentiate those?
Yeah, thank you for the very difficult question, very good question. So first thing is when we monitoring the permafrost temperature for the Arctic region, of course we know each region how much the warming. So that means definitely the tropical area we should do this similar kind of climatic impact for the tropical area. Maybe permafrost monitoring is one of the good candidate. But one of the biggest problems the area I show you about the snow is very impacted for the Kilimanjaro equator regions. So that means simply El Nino or La Nina for the ENSO cycle is strongly affect for the temperature. So that's considered part of the climate or considered not, but that's kind of another topic to thinking about, but that's one of the problems about the ENSO cycle versus permafrost. For the volcanic activity, unfortunately, most of the high mountains are active volcanoes. So that means very high, and typically in the most of the area in the Earth, we have about 20 degrees per kilometer of the geothermal for the Earth heating. But sometimes for the we monitoring like 200 degree per kilometer of the heat, 10 times higher geothermal. That still we have a borehole. So that means it's not really ideal place to do it. We wanna avoid it, but sometimes no way. Then we try to monitor for this. But one thing is yeah, the good thing is the most of the volcanic materials like Tefra or any material is kind of low thermal conductivity. Sometimes, Fairbanks nearby, only 100 meters away, but very still permafrost there. For them, the good things, the materials are good insulations than the other rocks. That case makes little help for us to study.
Yeah. And in that regard, that there, actually you mentioned about the grain size of the materials at the top of these volcanoes, particularly at Ampato, the picture you showed us, the most of the materials are gravel size. Okay, in terms of volcanological terms, it will be lapilli size. So it is more than 2 millimeters, less than 64 millimeters. And you mentioned that there is no ice, but there is still permafrost. The thing is that when we compare these kind of volcanoes, where the material is coarse grained, as compared, for instance, in Kilimanjaro, where there is more pervasive alteration and there are more clays.
Yeah, more sandy, yeah.
So how will be the development of permafrost in regards with the grain size?
That's a good question. Thank you. Yeah, I have a student for the volcanic thermal properties measured, and typically thermal conductivity of our monitoring site is minus 0.2 to 0.7 for the thermal conductivity, but of course, depend on how much wet the water content. Then once the water content higher, of course, much more higher thermal conductivity. So that makes a big difference. So that, but exactly, yes, once whatever the grain size is changing, thermal conductivity changing, I mean, the diurnal amplitude changing, everything changing by that. But much more than this changing, the water content is much more bigger. So I mean, if we have a dry permafrost, grain size is little different thermal conductivity, but still very low thermal conductivity. But if the ice bonded permafrost or very water rich, it's sometimes over one, the thermal conductivity is very high. So I mean, I'm more issue about the water content of or ice content of the soil is more than the grain size.
Actually, that's the point. With clay soils, there is a lot of porosity, but very low permeability. Yeah. And with the other coarse grained materials around the craters of volcanoes, there could be, if they are coarse sizes, there could be more porosity and very high permeability. And that's the point, how to deal with these differences along the higher volcanoes in Latin America.
Yeah, that's exactly the important. Very this presentation earlier I mentioned about how important study permafrost is a hydrology point of view. That's exactly related about each volcano has a unique characteristic and grain size and water content. That makes the permeability is very different. But that's we have to involve this understand for the glacier or volcanic interaction for the hydrology. That's water availability of the local people. That's our topic to study. Yes, and not the easy issue too.
Our friend Gino Casasa is perhaps online somewhere in the cyberspace, but he has been leading the group, the subgroup on permafrost, and rock glaciers of the working group on snow and ice of UNESCO. So one of the things, one of the issues that have come out from these groups is how to recognize, but it should be also before that, how to define a rock glacier. So with examples you showed, with ice covered with a lot of debris, you mentioned there those are not permafrost, but there are no they are not glaciers. So will them be defined as rock glaciers?
Yeah, that's yeah, again, that if we have a debris cover is thicker than the active layer, that's glacier ice or any kind of ice, which should be a permafrost. But the debris is thinner, very thin debris. Then active layer is always reach to the ice's interspace. That's not the permafrost. That's what I mentioned about, especially after 1995, our community defined for that. Then before 1995 is not clear about this definition. That's why it's just simply any paper before 1995, we don't have a such definition. So that means people using very gray zone to using for definition of permafrost. But now we have much more clear definitions. So then rock glacier definitely any rock glacier has a debris covers more than the active layer. We should say permafrost. Even the rock glacier, of course, yes. That's but if the rock glacier has a thin debris cover, that's still debris covered glacier.
Ok, no sé si hay alguna otra intervención aquí. Por favor, Lorenzo, déjame acercarte este micrófono.
Thank you very much, Kenji. I was wondering if you have noticed some correlation between the presence or absence of permafrost or the thickness of the active layer and the superficial presence of any type of pattern ground, polygons or stripes. Is there any correlations or they're completely unconnected?
Yeah, that's one of the biggest problem for me. I showed earlier about the nice, beautiful stripes. That's just a very cycle of the freeze-thaw cycles. It doesn't care about absence or presence of permafrost. But there is some presence of permafrost, some presence no permafrost. Until we digging, we don't know. Same things for the rock glacier or any rock field. Yeah, I think maybe you are more professional to understand any active meaning, maybe some movement you can detect by the vegetation or some other parameters, then you can see the movement. Maybe that meaning ice body is still in there or something. But for me, maybe we try to, hopefully we can understand your knowledge to using for the active some kind of futures movement. Then thinking about maybe permafrost exists there, then we like to drill there for but again, with the presence or absence of permafrost, we cannot tell anything until drill.
¿Alguna otra pregunta por aquí? ¿O en el ciberespacio? Hay una pregunta más por acá. There is another question because you opened the door to the solar system. In search of water, that's one of the issues some special agencies are looking for around, and perhaps permafrost could be a source for water that is needed for the conquest of the neighbor planets. However, how can we distinguish if what is made of what is making of the permafrost is water or could be other component? We know that from some other observations that at some places, like the outermost planets, the ice is made of methane. So how can we distinguish if periglacial processes or permafrost is actually made of water.
Yeah, that's a very good point. And actually, I'm involved with this kind of topic for the United States. Then I think that one of the things is that kind of back to the related for the Lorenzo, it is periglacial geomorphology is very important to understand the permafrost conditions, especially for Martian surface. Today, we have a very high resolution images available. But for example, if you see the log glacier, if you see the thermokarst, meaning permafrost, it isn't, right? That's I very strongly tell the terrestrial, the planetary scientists, because maybe million years ago you have a thermokarst, the ice melt, then you have some periglacial future exists today can see by the satellite. Is meaning no permafrost. Maybe long time already disappear, but all the landform still exists, something like that. So that means most of the periglacial process, periglacial futures we see today solar system is not active, not current. We cannot see anything except Pingo, which is my PhD. So Pingo, if we have Pingo mound, should be ice in. If this is mound is really the Pingo, ice must be in there, because if the ice disappear, you don't have a mound anymore. So that means the reality is, like ice wedge polygon, patterned ground, thermokarst, all the landforms, the periglacial land geomorphology is not proof anything about permafrost or water availability. But the Pingo is possible. That's I can tell. Then plus another issue is like Titan's surface as a liquid methane exists. Could be like liquid methane pressurized and make ice volcano type of the mound could be make it. So that means how to distinguish between the water, ice, and the methane. Sorry, that's another issue. We have to figure out this kind of temperature conditions, how the brine can be freeze or not, something like this. The Mars is kind of easier because we're closer to we know the temperature condition, the pressure, that we can see the liquid water, ice can how survive it. But if we go more further outer solar system, little more complicated issue involved.
Ok, pues muchas gracias. Thank you very much.
Thank you.
Lo despedimos con un aplauso y despedimos la transmisión en Facebook, en YouTube y en Zoom. Muchas gracias por estar presentes. Hasta pronto.